Welcome to the Public Exam Review for Advanced Math 3200. In today's presentation, we will look at Unit 1, Chapter 3 on polynomial functions. In this presentation, we will look at graphing polynomial functions when we are given the equation of the function and are expected to sketch the graph. Here we will focus on describing the relationship between zeros, roots, and x-intercepts of polynomial functions and equations. As well, we will sketch the graph of polynomial functions without technology. To begin, we will look at the multiplicity of zeros, or the roots of a polynomial function. In order to determine the zeros of this polynomial function, we need to let y equal 0 to get the zeros of the function, which are also referred to as the roots or the x-intercepts of the graph. So here we will have x plus 2 multiplied by x minus 1 multiplied by x minus 3 to equal 0. The zero product rule tells us that x plus 2 can equal 0 when x is equal to a negative 2, or x minus 1 equals 0 when x is equal to 1, or when x minus 3 equals 0, x equals 3. Notice that these values will give us the x-intercepts on the graph of the function. So we have one x-intercept at negative 2, another x-intercept at 1, and another x-intercept at 3. When you multiply the leading coefficients in each of these terms, notice that you end up with an x cubed value. This tells us, so you think about the x cubed value, and you know that you're graphing a cubic function in which the graph is a sideways f. Because the value of a, the leading coefficient, is positive, the sideways f will extend up into quadrant 1 and down into quadrant 3. And the x-intercepts are used to help sketch the graph of this function. Because we have 3 different x-intercepts, and a cubic polynomial function can only have a maximum of 3 x-intercepts, we refer to these as 3 single real roots, or 3 single real roots, where each of these zeros has a multiplicity of 1. In other words, the factor for each polynomial will only occur once. On the other hand, this example gives us the function y equals x plus 1 all squared times x minus 3. Once again, to determine the zeros of the function, we have to let y equal 0. So we have x plus 1 squared multiplied by x minus 3 to equal 0. This will occur when x plus 1 equals 0, when x equals a negative 1. But because it has a multiplicity of 2, we refer to this as a double root or a double zero of the polynomial function. The other root will occur when x minus 3 equals 0, and that's at x equals 3. The question asks, what effect does a double root, which is a zero of multiplicity 2, have on the graph? Notice here that the double root occurs at x equals a negative 1. At that point, the graph of the sideways f is tangent at any zero with a multiplicity of 2. So it's tangent at x minus 1, and the other single real root occurs at x equals 3. That factor has a multiplicity of 1. Another example shows a multiplicity of 3. We are still dealing with a cubic function, y equals x minus 3 raised to the power of 3. Notice that our graph is still in the form of a sideways f. To determine the zeros of any polynomial function, we let y equal 0, so therefore we would have x minus 3 all cubed is equal to 0. That will only occur when x minus 3 equals 0, when x is equal to 3. Because the 0 has a multiplicity of 3, we refer to this as a triple root. When you examine the graph of the function at that triple root, notice that the graph flattens. That's the word we use to describe it. The graph flattens at that triple root, at x equals 3 in this particular case. So anytime you have a 0 of multiplicity 3, there will be 3 real roots at a single point in which the graph will flatten at that point, but it will still pass through it. In the previous case, when you have a 0 of multiplicity 2, the graph will be tangent at that point. And notice that the graph does not pass through that point. It will touch it at only one place. So let's look at some examples. Here we are asked which graph represents the function f of x equals x minus 2 all squared times x plus 4. Again, to look at that function, you need to look for the zeros of the function by letting f of x equal 0. So here we have x minus 2 of multiplicity 2 multiplied by x plus 4 to equal 0. That will occur when x minus 2 equals 0. When x is equal to 2, we will have a double root at that point. So the graph would be tangent at x equals 2. The other root will occur when x plus 4 equals 0, and that's at x equals a negative 4. That's what we refer to as a single real root because it has a multiplicity of 1. So when you examine the graph, we have a double root here at 2 and a single root there at negative 4. So you have a single root at 4, and because the graph is tangent at x equals 2, you know that that is the double root. So the correct answer for this multiple choice item is A. In the next example, it says which function has degree 4? And you're told that the zeros are at negative 2 of multiplicity 2 and another 0 of 5 of multiplicity 2. So using the given information, if we have a polynomial function of degree 4, that tells us we're working with a quartic polynomial. And the quartic polynomial will be either in the shape of an m, if the value leading coefficient is less than 0, just to review what we did in the previous presentations. And if a is greater than 0, we will have a W-shaped graph. So in all 4 cases, we have polynomial functions of degree 4. However, if you look at the zeros of the polynomial, it's saying that we have a 0 at x equals a negative 2, and because it has a multiplicity of 2, we know that x plus 2 will be raised to the power of 2. So we can look for a double root at x equals a negative 2. And the graph would have to be tangent at that point. Notice in part A we have a single root at negative 2, so that eliminates A as a multiple choice answer. Similarly, we have a single root at negative 2 in B, so that eliminates B as a multiple choice answer. And in D, we don't have any root at negative 2, so D is also eliminated. So the correct answer here has to be C. Let's look to see if the other condition also applies. We're told that it has another 0 at x equals 5, and because it is of multiplicity 2, we know that x minus 5 will be raised to the power of 2 to equal 0. And again, there will be another double root in which the graph of the polynomial function is tangent at 5. And that is the case in part C. In example 3, which best describes the graph of the function f of x equal to a negative x multiplied by x plus 3 all squared multiplied by x minus 4. When I look at that function, I'm multiplying a negative x multiplied by x squared multiplied by x. And in my mind, I see that that leading coefficient will be a negative x raised to the power of 4. So we're dealing with a quartic function in which the value of a is less than 0. That tells me that the graph will be in the shape of an M. When the leading coefficient of a quartic function is less than 0, the graph will extend down into quadrant 4 and down into quadrant 3. So here we have an M-shaped graph which eliminates C and D as multiple choice items. So now we need to look at the zeros of the polynomial function. The zeros in this case can be determined when we let f of x equal 0. So here we have a negative x times x plus 3 all squared times x minus 4 will equal 0. That will only occur when x is equal to 0. That will be a single root at x equals 0. That condition is met in both A and B. When x plus 3 equals 0, we have a double root at x equals a negative 3 because it has a multiplicity of 2. A multiplicity of 2. So in this case here, you have a third root when x equals minus 4 equals 0, and that's when x is equal to 4. So that root occurs with a multiplicity of 1. So you have single roots there at 0 and 4 as opposed to negative 4. And the multiplicity of 2 occurs when x is equal to a negative 3, not when x is equal to 3. So the correct answer for this multiple choice item occurs at B. In example 4, which graph represents the function y equals a negative x cubed plus x squared plus 12x? Once again, identify the type of polynomial function you are working with. So here we are working with a cubic function in which the leading coefficient is less than 0. The graph will be a sideways f. And when you think about the end behavior of the function, because a is less than 0, the graph will extend down into quadrant 4 and up into quadrant 2. When you look at those the situations that we are presented with, we can now eliminate B and D as multiple choice items. In part A, the graph extends from quadrant 4 up into quadrant 2, and similarly for part C of the multiple choice items. So we still need to look at the zeros of the polynomial to determine the correct answer. In order to get the zeros of the polynomial, or your x-intercepts, in this case we let y equal 0. So we have a negative x cubed plus x squared plus 12x equals 0. To remove the negative in front of the x squared, we can divide or multiply both sides of our equation by a negative 1. When we do that, we have x cubed minus x squared minus 12x is equal to 0. You can factor this polynomial by removing x as a common factor. Outside of x squared minus x minus 12 equals 0. That trinomial can be further factored. The factors of a negative 12 that have a sum of a negative 1 are x minus 4 multiplied by x plus 3 to equal 0. Using your zero product rule, x will equal 0, or x minus 4 equals 0, which occurs when x equals 4, and x plus 3 equals 0 when x is equal to a negative 3. So in part A, we have a single root at negative 3, another single root at 0, and another single root at 4. So it appears that A is the correct answer for this polynomial, the graph of this polynomial function. Again, just notice that you have 3 single roots here which occur with a multiplicity of 1. A potential long answer question related to this, the graphing of polynomial functions, when you are given information to come up with your equation and then to produce the graph. We are asked to algebraically determine the equation of a polynomial function that has x equals a negative 2 as a 0 of multiplicity 3, and x equals 3 as a 0 of multiplicity 2, given that the function passes through the point -1, -8, and then we are asked to sketch the graph. Let's look at some key pieces of information here. The first piece of information is that x equals a negative 2 has a 0 of multiplicity 3. That tells us that if x equals a negative 2 has a 0 of multiplicity 3, then we know that x plus 2 raised to the power of 3 must equal 0. That will be one of the factors of the polynomial function. Similarly, we are told that x equals 3 has a 0 of multiplicity 2. So because of that, we know that x equals 3 will have a factor, x minus 3, raised to the power of 2, because it has a multiplicity 2. In order to determine the equation of the polynomial function, we have y equals a multiplied by x plus 2 raised to the power of 3 multiplied by x minus 3 raised to the power of 2. We need to determine the value of a in order to know determine the end behavior of the function. The other piece of key information that we are given is the fact that the function passes through the point -1, -8. We can use the coordinates of this point, -1 and -8, to substitute in for x and y to enable us to determine the value of a. So here we have a -8 is equal to a multiplied by -1 plus 2 raised to the power of 3 multiplied by -1 minus 3 raised to the power of 2. -8 is equal to a multiplied by -1 plus 2 is 1, raised to the power of 3 is still 1. -1 minus 3 is a -4, squared is 16. So here we have -8 is equal to 16a. Dividing both sides by 16, we have a is equal to a -1/2. So the equation of this polynomial function is y equals a -1/2 times x plus 2 raised to the power of 3 times x minus 3 raised to the power of 2. So that is the polynomial function that we were asked to determine. In order to sketch the graph, we can go directly to the roots of the zeros or the x-intercepts of the polynomial function. X equals a -2 has a multiplicity of 3, which means that the graph must flatten at that point. X equals 3 has a multiplicity of 2, which means that the graph of the polynomial function must be tangent at that point. Because the leading coefficient a is less than 0, the graph will extend from quadrant 4 up into quadrant 2. When you look at the graph of this function, or when you look at the equation of the polynomial function, you have x raised to the power of 3 multiplied by x raised to the power of 2. So this graph will represent a quintic function, in which the graph will be what I refer to as a squiggle. So another key point on the graph before we sketch it is to determine the y-intercept. In order to get the y-intercept of this graph, you can let x equal 0. So the value of y would equal a -1/2 multiplied by 0 plus 2 all cubed multiplied by 0 minus 3 all squared. So you will have y equals a negative a half multiplied by 8 multiplied by 0 minus 3 is a negative 3 squared is 9. So you have negative a half times 8 is a negative 4. A negative 4 times 9 is a negative 36. So your graph must pass through a negative 36 as well. So now to sketch the graph of the polynomial function, you begin in quadrant 4. The graph has to be tangent at 3. It will pass on through that y-intercept, and it will have to flatten around that triple root there at x equals a negative 2, and it will extend up into quadrant 2 and down into quadrant 4. So that is a sketch of the graph of this polynomial function. In the next example, we are asked to sketch the graph of y equals x squared minus 2x times x squared minus 4. Algebraically determine all intercepts, which includes both your x and your y-intercept. And then we will state the interval where f of x is less than 0. So let's take the polynomial function and put it in completely factored form first. So we have y equals x squared minus 2x multiplied by x squared minus 4. In the first factor, we can remove x as a common factor outside of x minus 2. The second factor can be factored as a difference of two squares, x plus 2 times x minus 2. Notice that the factor of x minus 2 occurs twice. So we say that x minus 2 has a multiplicity of 2, thereby we raise it to the power of 2, multiplied by x plus 2. So this is the polynomial function that we will work with. To determine the zeros or the x-intercepts, we will let y equal 0. So we have x times x minus 2 all squared times x plus 2 equals 0. That will occur when x equals 0. When x minus 2 equals 0, we get x equals 2. Because it has a multiplicity of 2, we know that that will be a double root, and the graph will be tangent at x equals 2. And then the other single root occurs when x plus 2 equals 0 at x equals a negative 2. So these are the three roots of this polynomial function. However, when you look at the coefficients that are multiplied, you have x times x squared times x. So that tells me that we're dealing with x to the power of 4, which is a quartic polynomial. Because the leading coefficient is greater than 0, we know that the graph is going to be in the shape of a W. The graph will extend up into quadrant 1, and it will extend up into quadrant 2 as well. We also need to look for the y-intercept here. So in order to get the y-intercept, we have to let x equal 0. So here we would have y equals 0 multiplied by 0 minus 2 all squared times 0 plus 2. And the value of y will equal 0. So if you have an x-intercept at x equals 0, it must also be the coordinates for your y-intercept as well. So now, to sketch this graph, the leading coefficient is greater than 0. So the graph will extend up into quadrant 1. X equals 2 is a double root. So here the graph must be tangent at that point. It will turn around and it will pass through x equals 0, which is a single root, and it will turn around again and pass through x equals a negative 2, because that is also a single root. To answer the last part of this question, we are asked to state the interval where f of x is less than 0. Less than 0 is the region of the graph that is below the x-axis. And it does not include any value that is on the x-axis. So the only region of this graph that is below the x-axis It does not include these x-intercepts, so I'm just putting hollow dots there, but it will be this region below. So in this case, to answer the question, to state the interval where f of x is less than 0, it's the interval between -2 and 0 with round brackets, because the x-intercepts are when the function equals 0, not when the function is less than 0. So that would be your solution for the last part of this question. As a summary of what we've discussed throughout this presentation, you could sketch the graph of a polynomial function using the x-intercepts, the y-intercepts. The degree of the function will help us to determine the shape of the graph, and the sign of the leading coefficient helps us to determine the end behavior of the function. The x-intercepts of the graph of a polynomial function are the roots of the corresponding polynomial equation. When a polynomial function is in factored form, you can determine the zeros from the factor. When it is not in factored form, you can use the factor theorem and the integral zero theorem to determine the factors. When a factor is repeated n times, the corresponding zero has a multiplicity of n. The shape of a graph close to a zero of x equals a multiplicity n is similar to the shape of the graph of a function with degree equal to n of the form x minus a raised to the power of n. For example, the graph of a function with a zero of x equals 1, multiplicity 3, as you can see in the provided graph, will look like the graph of a cubic function, which is of degree 3, x minus 1 raised to the power of 3. And notice that the graph flattens at that point where x equals 1. Polynomial functions change signs at x-intercepts that correspond to zeros of odd multiplicity. The graph crosses over the x-axis at these intercepts. Polynomial functions do not change sign at x-intercepts that correspond to zeros of even multiplicity. And what they mean by that is that the graph will be tangent when we have a multiplicity of 2 or a multiplicity of 4. The graph touches but does not cross the x-axis at these intercepts. It will be tangent to it. If you have any questions related to the content in this presentation, please pose your question in the question forum. Thank you very much.